G'day and welcome to the third of the 4 videos I'm making for one of my subscribers, Danishan. Thank you for your list, which I have here. I've already, if you've been following the series, I've already proven 2 trigonometric identities. This is now the first of 2 videos where I solve trigonometric equations. And the first one that Danishan gave me is this: to solve tan y minus 2 equals cot, or the cotangent of y. Now, we've got a restricted domain here. Y lies between 0 and 180 degrees. So we're talking degrees rather than radians, and it's fairly restricted to half a cycle. It's very nice looking at this. It's just a simple y. There's no y squared or 2y or anything like that. There's no phase shift, y plus 3 or anything inside. Simple tangent, simple cotangent. First thing that strikes me looking at this is that there's a connection between tangent and cotangent. The cotangent is the reciprocal. Now, experience tells me that when I have an expression like x plus 3 equals a reciprocal of x, these give me quadratic equations. It doesn't mean I've got to solve that way, because you can see when I multiply both sides of this by x, I get x squared plus 3x equals 1, and I would have to attempt to solve that. So I could solve this using quadratic equations. An alternative way is that when you have tangents and cotangents, if you convert everything into sines and cosines, you can then resolve the equation. I think you'll still get a quadratic anyway, but it will just be expressed in a different way. So we're going to leave them as tangents and start off this way. Change the cotangent to 1 over tan. Multiply both sides by tan y, and I'll get tan squared y. Minus 2 tan y is 1. And since it is a quadratic equation, I'm going to bring the 1 over because we traditionally solve quadratic equations by setting them equal to 0. So we've got tan squared y minus 2 tan y minus 1 equals 0. Okay, we've made our first observation and converted it into what we thought was we had a quadratic. At this stage, if you're not comfortable with it, you can substitute tan y for u or x or something, so you've got a simplified looking quadratic, but it is just a quadratic. If it was plus 1, we'd have a perfect square. You know, x squared minus 2x plus 1 is just x minus 1 all squared. But we don't, we've got a minus 1. And the question is, can it be factorised or not? Well, if you're not sure, you could check your discriminant. B is worth negative 2. And A times C is worth negative 1. So that's 4 plus 4 is 8. That means that when we use the quadratic formula, when we find the zeros or the roots, we're going to have a square root of 8, which is not rational. So trying to factorise it using our normal factorising techniques, not going to work very well. So let's use the formula. I don't care whether you call them zeros or roots, but we'll write this. Tan y would equal minus b, let's write it, plus or minus square root b squared minus 4ac all over 2a, which is minus, now the b was negative 2, plus or minus the square root. Now we've already worked out this discriminant, that's worth 8, square root of 8, and 2 times a is the coefficient of tan squared, So it'll just be 2. Now I hope you realise there are a few little techniques being used here. Root 8, of course, is root 4 times root 2, because 4 2s are 8, and root 4 is 2. So simplifying radicals or surds is another skill we need. So minus or minus and negative gives you a positive 2. Plus or minus, root 8 is worth 2 root 2 over 2, and dividing by 2 gives you 1 plus or minus root 2. So this is not super standard. We often give fairly simple trig functions to solve, like tan y equals 1 or root 3 or something like that. This is not a pretty number. So, well, actually it's 2 numbers, isn't it? 2 solutions. I don't have any more board to work on, so I'm going to rely on the fact that you can move back and forward in the video. I'm going to erase this and use this result. I'm going to write tan y equals 1 plus or minus root 2 on the top, and we're actually going to solve this equation in this domain to find what angles, what y values will work. So let's have a look at that. Well, let's see if we can find angles that will make this statement true. Well, actually it's a pair of statements, isn't it? So let's write them separately. We can write tan y is 1 plus root 2, or tan y is 1 minus root 2. How do we solve it? Well, we'd love to have y equals, and we have a method for getting rid of tangents. A lot of students don't understand why or what the process is, but just a little bit of an aside. If you had x plus 1 equals 3, and we had to solve that equation, you'll get rid of the 1 by subtracting 1. If you had 5x equals some number, 30, we would get rid of this 5 by doing the opposite of multiplying and dividing by 5. Later on you learn that if you have x squared equals some number, we solve it by taking the square root of both sides. Or alternatively, if you had that equation, you would square both sides, because squaring and taking the square root are what we call inverse functions. They undo each other. Later on you'll learn things like exponentials and logarithms. So for example, e to the x equals 7. We would take the logarithm of both sides, because the logarithm undoes the exponential and leaves an x. Now, we'll talk more about that another time in other things. But when it comes to trigonometric functions, the inverse function for a tangent is tan to the minus 1, what we call an inverse tangent. And we would do this to both sides of the equation. We do it here as well. So we would end up with y equals the inverse tangent of 1 plus root 2, or y equals the inverse tangent of 1 minus root 2. Okay, I shouldn't really be using up my board doing this, but I just find it helps students to see this occasionally. Now, at least we've got y equals, but what does an inverse tangent look like? It's an angle. These are the angles that we want. Now I'm going to talk about our unit circle. If this is a unit circle, 1, 1, negative 1, negative 1, 0, and we draw a tangent here, then if we find the position 1 plus root 2 up the tangent, there's 1, that's 1 unit long, so 2 units long would be there, and 1 plus root 2 is about 1.4, so we're up to about 2.4, so 3 will go up here. So this value, 1 plus root 2, would be about here. And if I drew this line down, oh, that's terrible. If I drew this line down here, in this right angle triangle, you could see that this distance, 1 plus root 2, over 1, that's why we used a unit circle, is the tangent of this angle. I'll call it y. So tan y is opposite over adjacent, which is 1 plus root 2 over 1. There it is. It's tan y is 1 plus root 2. So this is the angle we're after. And our calculator will give it to us. And it will also imply this is an answer as well. I'll talk about this in a moment. I have a calculator here, and turning it on, I check that it's in degrees because we're talking in degrees. And I calculate the inverse tangent of 1 plus square root of 2, and my answer is 67 1/2 degrees. (67 degrees 30 minutes). There it is. And I think you can see, I tried to do this to scale, and you can see that it looks pretty close to 60 or 70 degrees. We could accept this angle as well, except we must go back and look at our restricted domain, because really we could just keep going round and round and round and round, and every time we came back we could do 360 degrees plus another 67.5, and then we could do 2 cycles, 720 degrees plus 67.5, or we could do 180 plus 67.5 because vertically opposite angles. So we could have an infinite number of these depending on cycling round, but we only want between 0 and 180, between here and here, and that's the only time it hits this line. If this was 360 degrees, we would get a second answer. But that's it. That's the only answer to that. What about this one? Where is 1 minus root 2 on here? Well, root 2, remember, is about 1.4. 1.414, something or other. 1 minus that is minus 0.41 something. So there's minus 1, negative 1. That's the distance, negative 1. So negative 0.4 is about here. So we're now looking at this triangle, this right angle triangle. We're looking at this distance over 1, this angle. Now I think you can see it's going to be a negative angle, or if it continues through here, I should change colours, shouldn't I? I'm not sure if this will help or not. Let's try red and blue. Okay. So, this is one angle, going backwards, going in an in a clockwise direction is a negative angle. Going anti or counterclockwise, we would get this. We could go around here and keep going. It really doesn't matter which way we go. An infinite number of answers. The only one that's going to be between 0 and 180 degrees, however, is not this end, but this end. It's this angle, just before we get to the 180 degree mark. And I think you can see this looks like a small angle, I don't know, about 25 degrees or something like that. Let's check it out. Inverse tan, so shift tan, 1 minus root 2 gives me, should be back to blue. Oh, actually I might leave it in red. That's such as it is, this thing has picked up some blue there. Negative 22 degrees 30 minutes. Gee, that's awful. But that is not in this domain, is it? That one is measuring this angle here. And if that angle equals this one, this is 22 degrees 30 minutes here. So if I want to know the angle from the positive x-axis around, I've got to get 180 degrees and take away this. Well, fortunately I've got minus 22 degrees 30 minutes here, so I'm just going to add 180 degrees. And that gives me, I'll just put this as another answer, 157 degrees 30 minutes. And we don't accept that because it's not in the correct domain, so our only answer here is 157 degrees 30 minutes. And putting it together, we would say, therefore, this was quite a long problem. Y would equal 67 degrees 30 minutes. That's one answer. Or, you can write the word or you can just use a comma, 157 degrees 30 minutes. Now at this point you might be tempted to stop, but I would encourage you just to, let's draw a line. We've got our answers, but why not check that we're right? It shouldn't take long, not with a calculator. So we started off with tan y minus 2 is cot y. Okay? Let's put this number in. What's tan of this? So, tan, 67 degrees and 30 minutes, minus 2 equals, now I've got an interesting decimal. There are a few ways we can do this, but let's not. That's looking suspiciously like 1 minus root 2, isn't it? And let's do, cotangent is 1 over tan, so let's do 1 over tan this. I'll just do it simply without the fraction. 1 divided by tan of 67 degrees, 30 minutes, equals, and guess what? And just that little check makes sure that I've got the right result. And during a test, if you've got the time to do it, you can often do this in 20 seconds or 30 seconds and be very confident you've got the right answer. Of course, if you do that again, I'm not going to bore you with the details, but you can put that in and check that both sides match. But that's the solution to that problem. It's a little bit more, a fair bit more difficult actually than a lot of common school test problems, because it developed into a quadratic, first of all, which gave us 2 answers. The 2 answers turned out to involve radicals. They weren't rational, and they certainly weren't fractions that are familiar to us from our common triangles. So it led to some rather interesting calculations. I hope that's been of use. I certainly hope it's answered your questions, Danishan, about the nature of the problem. We have one more to go, another trigonometric equation to solve, and I hope you're looking forward to it. If you want to see it, click the subscribe button and you'll be told about it when it appears. And as always, I really appreciate your clicking the like button and leaving a comment. And thank you for watching.